And we are live. Hello, everyone.
Hey.
I'm just double checking, Edgars, if we're live as always, so that everyone can see this live stream on X, and we are live, confirming. Well, hello, everyone. Thanks for joining another live stream, another GenLayer live stream. Today is a really special one. We're going to cover what powers GenLayer. My name is Tony. I'm the head of content and community for GenLayer, and I have with us today Edgars, who is the CPO and co-founder. So there's actually no better person to describe the GenLayer stack than Edgars. You've spent a lot of time looking into this. I know we had a lot of conversations previously, so I'm happy to have you here, Edgars.
Thanks for having me, Tony, as always.
Thank you. Well, before we start, as every one of you knows, we had a few announcements recently. We had the Caldera partnership announcement. We're also going to have Caldera, James from Caldera, on this live stream next week. So we are kind of preparing what powers GenLayer, going into the whole ZK Sync roll-up conversation with Edgars today, and then next week we're kind of setting the stage for Caldera coming on and also explaining how the partnership with GenLayer and Caldera works, how the technical implementation worked. So yeah, I'm also looking forward to that, and I think that it's important to clear the basics kind of today. I know a lot of people in the community have also been asking how the GenLayer tech stack works. So yeah, I'm pretty pumped to talk about this with you today, Edgars. For all of you who are in our Discord, as you know, you can download the POAP Home app. I'm just trying to pass the link here. You can download the POAP Home app and mint your POAP at the end of this session with our secret pass key, which I'm going to share in about half an hour to 40 minutes. And feel free to also check out, we have a new campaign launched on Interact just like an hour ago. You can find it on our X profile and participate. Also an invite campaign on Discord, so check it out. A lot of XP, a lot of POAPs to be distributed. Okay, that being said, Edgars, I wanted to kind of highlight how GenLayer works. You know, some decisions leading into you guys, Albert, you and JM, deciding on, you know, what you want to build on your own, what you're kind of using from ZK Sync or from Caldera, and how it all works together. So just a very short recap. I know that a lot of people have been asking. So GenLayer is a trustless decision maker, basically an AI-powered trustless decision maker. And what that means is we are implementing a completely new consensus mechanism, which is called optimistic democracy. Obviously, there's way more to that. There's also GenVM and intelligent contracts, how we call them. But if you're looking at optimistic democracy, it's kind of the heartbeat of GenLayer. And what it basically is a DPoS, delegated proof of stake system, where each validator is connected to a different LLM. Those can be open source, those can be closed source, and validate transactions. Those transactions can be non-deterministic, which means, for every same input, you don't get the same output. If you ask an LLM today, what's the probability, how are you, what's the weather in Berlin, what's the weather in Berlin today, what is it tomorrow? It changes constantly. So to interpret that data, Edgars, Albert, and JM have developed a system that can actually, in the most accurate way, answer these subjective or non-deterministic questions. So that's kind of a recap of what we know so far. And now, Edgars, if we go into the tech stack, we or I would really like to understand, like, I'm a classic user, I have this transaction going through into GenLayer. What happens next? Maybe we can draw some parallels in Ethereum. Usually the transaction would be picked up by a validator. How does it work in GenLayer? And maybe then we can double click on some of the tech spec and the technical infrastructure needed for that.
Yeah, thank you, Tony. I think let me take a step back first a little bit and kind of set the stage for all of this.
Yeah.
As Tony said, GenLayer is a system for unbiased, decentralized, trustless decision making, meaning it can resolve some dispute, let's say, and tied in with that also then move assets. It needs to be self-enforcing and it needs to be neutral, and these are the kind of foundational assumptions that we started with, which led us to some, let's say, non-negotiables. And then the actual architecture of how we built it is quite, I would say, unusual. It's very interesting. So I'm also excited to get into that and explain how we got there. But I will let's say build it up for all of you. So we start from these assumptions. We wanted this AI powered decision making system that could actually be neutral, could make decisions that involve money, that two parties that don't trust each other could trust the same way you can trust a paper contract that's resolved by a human judge. The same way you can trust a smart contract, which in that case is resolved by deterministic code. So always the same exact thing happens, and you have many validators that can, well, basically double check. They all have to agree on the exact same outcome. That's what happens in any traditional blockchain. And how do you achieve this same kind of property with large language models, with natural language AIs, which are much more flexible? They can make much more subjective decisions. They can deal with context, kind of common sense, for lack of a better word. They can infer missing information. They can adapt to changing circumstances. But the problem is, as Tony said, each individual one of them is not a perfect decision maker because they make mistakes. They're probabilistic. Sometimes they're right, sometimes they're wrong. And they also have their own biases. Some models don't want to talk about certain topics, or they have a certain preference for certain kinds of outcomes. Whatever happened in their training data, and it's actually not trivial to even know what those are. The people training these models, it's not like they choose to have specific biases. It's hard to anticipate necessarily everything.
The developers don't even know themselves, right? Like that's
I always like to say, you sometimes see people asking questions, why are we building AI for generating pictures instead of doing housework? And my answer to that is, well, I agree. I'd love to have an AI robot at my home, to help me with housework, do random stuff like that. The problem with that is that AI, I would say, is almost more discovered than designed. It's not like somebody sat down and decided they really wanted to build specifically an image generating AI. It was more like people were researching different applications of deep learning, these very large neural networks, and just kind of trying different areas and trying different techniques until they found something that works. And it turns out, these cases where you have a ton of data, where you can just get a billion images from the internet, or all the text on the internet, and figure out a way to kind of do an unsupervised training run, train these AIs. Well, it turns out that's what you get out of it. So that's why these are the first use cases we have. But basically, every new generation of the model, the creators don't know how it's going to perform. I mean, they have some guesses, I'm sure, but they don't really know until they train it. They find out, and then it's a process of discovery, more or less than a design. So anyway, that's a complete tangent, I guess. But to tie it back to the main point is that they come out with personality. I mean, sure, everybody saw GPT. Well, I don't remember their naming. It was like maybe one of their latest 4 O's that came out extremely syncopathic and would agree to everybody about everything, no matter how deranged and crazy things you were asking it to do. They have personality. They have bias. Basically. So you don't want just a single one of them to make a decision in terms of the model itself. But even aside from that, you also have this practical problem. If you and I want to have AI make a decision for us, well, who is actually going to run the AI in terms of actually running the code and producing the output? Well, is it going to be you or me? Probably not. If it's a really high stakes decision, you wouldn't really trust me to run the AI on my machine and kind of say, this AI says that I'm supposed to take all the money, right? That doesn't really work. It needs to be neutral between us. Is it going to be one of these centralized entities? Well, it's also not very transparent. It's not really trustable. They change their models all the time. They have their own policies, or who knows, somebody might bribe them, even one of us. Again, it's not really trustable. You really want a system where many different independent entities work together and they're kind of able to check each other's output to effectively get this wisdom of the crowds effect. Very similar how you build a lot of systems in crypto that are too complex for deterministic code. Then you get a number of people like Kleros, like UMA, like all these systems. Instead of trusting one person, you get a number of people to work together on this answer. This lets you cancel out all the individual biases. It makes it much, much harder to attack because now you're not attacking one person, in terms of bribing them or coercing them or somehow otherwise compromising them. You have to attack, in our case, like 1,000 different validators at the same time to affect, or let's say half of them, because it's based on majority voting. So makes it much harder to attack, makes it much more reliable, makes it much more adaptable, and it really lets you go from this 99% accuracy on some of the tasks, I would say already. But sometimes they'll still make mistakes. Well, by having them check each other's work, you can get much higher levels of accuracy, and by adding more and more validators through the appeal system, you can get much higher accuracy. So these are kind of the assumptions that led us to design our system. We need not one AI, we need many different AIs working together. That is how you achieve them being able to make the decision. So practically different validators running different AI models. So that's an essential part of the design. That's the core part of the white paper.
One essential thing I think, Edgars, that you mentioned is they all have their biases, right? And that's, I think, an important thing to understand is no matter, what intelligence, it still has their bias. It's not a question of how intelligent is the system. It's the question of, whatever you compare it to, it could have an IQ of 100, but also of 150. That doesn't mean that it doesn't have biases. It's intelligent, but it still has biases.
Because bias is more than that, even it has its own goals, right? Just because we find the smartest guy in the room doesn't mean we can trust him to make the decisions for the benefit of all of us or even any of us, right? He has his own interest potentially in my mind, and or he might be more interested. I might have bribed them, or it's an entity that has its own also potentially preference, or whoever is in this case running the LLM. LLM itself just maybe has biases, or maybe you can train some secret biases into it. That's also a potential possibility. But for sure, the entity that's running the AI has some biases, right? OpenAI is a company that's tried to maximize. Well, I guess it's it's like this non-profit with for-profit with a non-profit. Anyway, the for-profit entity is trying to maximize shareholder value, right? Shareholders don't include all of us, right? So that already tells you that they might not make an objective decision. So how do you get a system where you're able to cancel out these effects and make, let's say, you're trying to make objective or at least trustless, neutral decisions that don't benefit any specific party. Instead, they try to follow as accurately as possible the specified contract.
Yeah. Okay, I see that we already have a few questions. I'll just like to wait until we get to the part where I think they're perfectly fitting. So what you just said, Edgars, okay, how do you take this and implement it into a like a DLT, right? Like how do you implement it into a blockchain? Going from, where do you even start? Like, okay, it's a delegated proof of stake system, but how did you come up with this idea?
Yeah, so exactly what I've just described is very high level. It's very abstract. And let's say when you have to actually go and build it, there are many, many other decisions that you still have to make in terms of, how do all these validators communicate with each other?
Yeah.
Where do they store the state? How do they affect world? Nowadays, very important question, how do they interact with the rest of the crypto ecosystem, right? It's not anymore about these isolated platforms, where everything happens on that platform. There are rollups and bridges and everything is interconnected, and you need to be able to move back and forth and affect everything across the ecosystem. So that's an important part of it. So a lot of these decisions that go into actually taking this very high level idea and implementing it. And basically, well, all of us co-founders, we've been in the crypto space for a while. I joined professionally in 2018. I mean, I was using it way before that, for playing around, for exploring. It was really interesting tech, but professionally, I joined crypto in 2018 at Radix DLT, which is another layer one blockchain smart contract platform, kind of infinitely scalable, horizontally scalable. I think their tech is very, very interesting. But there, let's say I got the opportunity to learn a lot about what goes into actually building a blockchain, building a distributed ledger technology, I guess, to be more precise. What are the components? How does it all fit together? How do you think about the economic design, which is a core part of the design, right? These systems, all these crypto systems, are based on economic incentives to kind of reward or punish incorrect behavior and achieve some sort of security guarantee, just based on the economic side of it. So that's where me and one of our co-founders, our CEO Albert, we were able to learn, a ton about how these kind of things work. I mean, Albert was at NEM before that, so we've seen quite a few technologies in our careers in crypto. So what we realized pretty quickly is that there are two ways to build something like this. You could either start from complete zero and build it from the ground up as a completely independent system, which has some advantages. Of course, you have full control. You can full control over everything that goes into the protocol. You can strap on different kind of consensus mechanisms that happen in the lower level, which is basically how the validators can agree, at least on the objective things that happen. Validator A voted yes or no in this scenario, or proposed this answer, these kind of things. And you get to build the entire stack, so it's potentially advantageous. Basically, the control you get, it gives you a lot of flexibility. At the same time, there are a lot of disadvantages, I would say, nowadays to this approach. I'm sure all of you have heard the term modular stack in crypto. It's been quite hot for the past couple of years, and the reason it's been hot because it makes a lot of sense. There is the saying in the startup world, which is that you should focus on what makes your beer taste better, right? If you're in the business of making tasty beer, or I don't know if your goal is to make it tasty, but very marketable beer for certain kind of taste. What your edge is, what hopefully your secret sauce or whatever you're adding to your beer is the key ingredient that makes your beer taste better than all the other beers. But you don't really care about what kind of truck delivers the beer to all the bars where it's distributed. You don't really care, if the building is built from concrete or from wood, aside from the fact that it doesn't fall on your head, right? These are all the kind of things you typically outsource to somebody else. You just pay them a bit of money because they're the expert in doing this kind of thing, so that you can actually focus on the one thing or the set of things that actually give you the edge, and you outsource everybody else. And classically, this shows up, it used to be that every company used to have a big mainframe in their basement, right, running their servers, and then everything moved to the cloud, right? So instead of having to, run this complicated machine and maintain backup power and alternate internet connections, and Sunday night it catches fire or everything goes wrong, right? Instead, you're just paying a bit of money to Amazon or Google to run the server in the cloud. They take care of it in these massive data centers. They have the best people in the world to do that. And maybe it's a bit more expensive than optimizing it, and maybe at some level you would then start to in-house some of these things. But when you're a startup, absolutely you want to focus on the things that are really interesting to you, and use other parts of the stack that you already know about. I mean, this shows up even in just programming. That's why a lot of people are building in languages like TypeScript or Python, because you have millions and millions. Well, I wonder if even billions. I haven't checked the numbers, but many open source packages and tools and everything that you can use, frameworks, everything. So you're not rebuilding a web server from scratch again. You just pull in Next.js, whatever, and that gives you all the routing and everything else that's the same basically across every application, and you just focus on the screens and the databases that are specific to your application, the functionality of your application. So the modular approach in crypto follows the same path. When you actually take a distributed ledger, a smart contract platform, it doesn't have to be smart contracts, but typically nowadays all crypto platforms are, including in our case, we call them intelligent contracts. They're more powerful, but same idea. It's some programmable. Instead of just transferring assets like Bitcoin, it's more flexible. It's more programmable. You can do an open-ended set of things. So when you want to build something like that, there are actually multiple kind of layers that go into that that can be actually split apart and outsourced to a layer that takes better care of that, such as such as transaction ordering. That's one of the more fundamental things a ledger does. This is what kind of deals with a double spend problem. Let's say I want to trick somebody. I only have $5 and I want to spend the same $5, send them to Tony, and go buy this very tasty beer also in one of these shops, right? So at $5, I'm trying to use them twice and actually pretend I have $10. Well, how do you resolve that? You need to know which one happened first, right? Did I send first to Tony or did I first send to the beer salesperson, right? This is going to tell you which history kind of happened, and the other one is going to get rejected. The other transaction is going to reject it. So transaction ordering. Data availability is related. You need to know the history of the blockchain for you to be able to construct a valid next transaction. If you don't know that, then even if you know your own balance, you might, or maybe you don't even know your own balance, but you kind of need to know what the current state is to be able to make changes to it. It gets a bit more technical at a low level, but essentially something like that. So you need all these different kind of layers that go into a blockchain. And we have all these different projects that have actually gotten really good at being a specific layer of the protocol, such that you can actually use these other layers and focus on the thing you specifically want to do.
Let me ask you a question here, Edgar. So everything you just shared, these layers, execution layer, a monolithic blockchain was all doing that on one layer, right? So execution, data availability, like everything was on one layer. And that's why, if you remember, we had the blockchain trilemma. And that's why we kind of hit our limits in certain regards, right? Like you can't scale Ethereum to infinity without layer 2s. You need to make kind of trade-offs on that. So everything you said is referring to the modular blockchain right now, in which you can kind of plug and play, like choose whatever you need to kind of build your blockchain.
Yeah, exactly. It's kind of like that. The scalability trilemma, it has some assumptions baked into it that actually don't mean it necessarily applies as broadly as some people think it applies. And that's why you're actually seeing some really scalable blockchains, either ones that scale horizontally or ones that are just really fast, or there's a lot of hidden assumptions in that scalability trilemma. But in some way, yes, you always are making some trade-offs in some areas, at least between some variables. The other thing about this modular approach is, well, I mentioned the fact that it's really important nowadays that a new chain is actually part of the broader ecosystem. Meaning, if you have some tokens on Ethereum or on Solana or on Sui, or all across the ecosystem on all the different other layer 2s that are out there, if you launch something completely new and it's entirely disconnected from the outside world, it's also not going to be very useful to other projects, right? If there's a prediction market on Ethereum that wants to use GenLayer for resolution, well, there needs to be a really good bridge between Ethereum and GenLayer, so that we can have messages going back and forth, and you can receive the answers from a GenLayer contract. If you want to use it for dispute resolution on Base, right? Again, you really need a good connection to there. So that was another driving factor that makes it easier with this modular approach. And I'm going to go into more detail, basically how we've architected this, but it makes it easier to achieve this sort of goal. It also enables us to build it more securely and more quickly, let's say by relying on these tried and true tested layers in our chain. It makes it an easier engineering challenge. Like I would say all of these problems are nowadays solved. How do you build a layer 1? It's a solved question. People are still pushing forward the speed, let's say, of it is the main thing, and the cost, driving down the cost. But at the same time, these are solved problems. You have pretty good answers if you wanted to do this, but it's a big engineering challenge to build this all from the ground up and test it and audit it and make sure all the bits and pieces fit together. So again, if you can reuse some of these existing layers, you're going to have battle-tested components that have huge teams of people already working on them, pushing them forward on their own. So it gives this extra reliability that we can achieve through this approach.
Okay, so taking all that into account, now let's transfer that to GenLayer. We have a blockchain that is capable of, kind of giving developers the power to build dApps that can think, that can reason, that can act on their own. We call it intelligent contracts. And how this is enabled is by what we kind of started off with, which is, it's a consensus mechanism called optimistic democracy. So you have all these LLM, connected validators. First off, where do these validators live? And I think I will just highlight one question, which is from Gingo. And maybe you can also go into that. Can GenLayer technically make it possible for current validators of a chain, specifically ZK Sync, to also become GenLayer validators, perhaps by adding a new function?
Yeah, this question specifically goes more into how ZK Sync works, which is that ZK Sync doesn't actually have validators as such. So ZK Sync works through a sequencer, one single sequencer that posts cryptographic proofs that basically show it executed the chain correctly. So it doesn't actually have validators. So in that sense, no. In terms of other validators becoming GenLayer validators, also there's not really any overlap. You need to spin up the GenLayer validator and sync with the GenLayer chain and join the GenLayer network. So it's there's not much overlap in that sense. I mean, of course, the validators we're working with for a testnet, upcoming testnet, they're all validators of many chains. So you transfer a lot of this expertise that you have from running other chains, but there's no cross transferability specifically with any other chain directly. I think it's worth then explaining why we actually chose ZK Sync. It's mentioned in the chat. That's the stack we chose basically to build on top of, and I can talk you through what it gives us basically, which is we have all these GenLayer validators. So that's the essential part of the network. All these different validators with different large language models. Well, they need some way to communicate, and they need some way to implement this decision-making procedure that I've described, where, I haven't described it in detail today, but effectively one of them gets randomly selected, they propose an answer, then 4 other validators in the first round vote on this answer, if they agree or disagree, right? If they disagree, they try again. If they agree, then it can be appealed, bring in more validators, right? All these rules of the game, basically. You can think of it almost like a board game. And they're also then rewarded or punished. They, based on what happens, they receive part of the transaction fees if they're voting correctly. If not, they can be punished. If they misbehave in a very serious way, then they can be slashed, which means they lose a bigger part of their stake as a bigger punishment and disincentivize what's happening. So you have all these rules, this kind of flow chart of all the things that could happen. You need to find a way or build a way that enforces these rules between all these validators across all of them. And the way we've chosen to do this is by building on top of a ZK Sync rollup. So an elastic chain, as they call them. It's a rollup that's specifically for GenLayer, the GenLayer chain that is running on the ZK Sync stack. So it's secured by Ethereum, so rolling up to Ethereum, and it's secured by cryptography. So the sequencer that's creating this chain, the ZK Sync chain, is posting these zero knowledge. So that's what the ZK stands for, zero knowledge proofs to Ethereum. And the zero knowledge proof, it's a neat bit of technology basically that lets me prove to you that I've done something correctly without you actually having to check all the work. Basically, I can prove to you that I executed Solidity code correctly without you having to go and check all the transactions that I actually did, because I wouldn't, until the end of the universe, I would not be able to produce a proof unless I really did it correctly, essentially, at a very, very abstract level. It's a fun analogy that actually helped me understood it is, imagine there's like a huge maze with only one correct door. There's a million different paths through it, and there's only one door that actually lets you through it. One path that lets you through it. Well, if I give you 5 minutes to get through that maze, and then I turn around and I see, oh yeah, you got through that maze. Well, you've proven to me that you know which path to take. There's no way you could possibly have tried all the million different paths without having to reveal to me which one is the correct path. That's one analogy that actually helped me kind of understand how something like this could work.
Yeah.
But in practical terms, what this means is zk-casing gives you solidity secure and efficient with high throughput EVM block space. So you can run normal Solidity contracts, the same as on Ethereum, the same as on all Ethereum rollups, secured by this zero knowledge, by this cryptography technology. It's high throughput, it's very efficient. And we use this layer for encoding and enforcing all of these rules of the game. So effectively, this layer, it has what we call our consensus contracts. And these are all deterministic contracts. So it's a normal blockchain, like all the other rollups, like all the traditional blockchains in Solidity. And these contracts, well, they don't understand anything about AI. They don't understand anything about web browsing. They have to be deterministic. But the rules of the game, so not the outcomes of the game, but the rules of the game are deterministic. Okay, there's a new transaction. It gets registered on the zk-sync layer. This means, okay, one of the 1,000 validators based on verifiable random function needs to be selected to be the leader. Okay, and now it has like a minute to post its provisional result. If it doesn't post the result, then it's idle, then we need to slash it and replace it with somebody else, right? And you keep having these rules. Okay, now there's the result. Okay, now the validators need to vote. Well, if it's a majority, then it's accepted. If it's not a majority, then something else happens. All these rules are entirely deterministic. Now, this contract is not going to understand anything, about what's happening in the game. Oh, there's some prediction market that's being resolved.
Sorry to interrupt you, Chris. So what you're saying is by entirely deterministic is every validator, so when a transaction comes in and what we call it the leader validator picks it up to execute it, every validator and every step of the process is determined so that you know what's happening next. So the leader is going to be chosen, the leader is going to pick up the transaction, execute the transaction, post, the other validators are chosen, the other validators execute the transaction, check for equivalence. So everything is kind of, set in stone. Everyone knows what to do. That's the part that's basically as in any other blockchain, right? Everyone knows what to do. Everyone follows the rules. If you don't follow the rules, you're eventually going to get slashed or, you drop out of the pool. But then the part which is non-deterministic is within the execution of the transaction and not even within the full transaction because some parts can still be deterministic, right?
Yes, exactly. So the way I like to imagine it is to forget about AI entirely and really imagine it as a system of people, or as I said, even a board game, relatively complex board game, but not, the most complex board game, to be honest, if you play some of these. They're called Eurotrash board games. Some of them get very, very complex. I would say even more complex than that. But yes, it's like a game, a system of rules and rewards and punishments that is entirely deterministic. What is not deterministic, how do I say? So let's say you don't know as a validator, so you have to produce some answer. What answer you produce, that's the non-deterministic part. So that's where you look up what the contract is in this address that's registered in a previous transaction. You look up what you have to do. You maybe have to go to the internet, so that's non-deterministic. You maybe have to run your LLM. That's non-deterministic. You don't know. You produce some answer. Or again, thinking about people. You're one of the judges or jurors in this network, basically, and the rules of the game say, oh, now you're the leader, and here's the task. What was the result of this football match last night? So you the juror in the system, well, you will look it up and you will post the result. But it's just like from the rules of the game point of view, you could post anything. It's just there's then the next rules. Okay, in the next round, then everybody's going to vote on your answer and see if they agree with your answer. Again, you can just imagine five people around the table. I've proposed that it was 1-0, and then you all pull out your phones. You find on BBC, oh yeah, I agree. This is the correct result. Or no, this guy is wrong. He needs to be punished, right? He needs to be replaced. Something. Either he's cheating, or he's just drunk. He doesn't have the right answer for whatever reason. You can't really tell often whether somebody's malicious or just incorrect. Making mistakes. It's the same.
Technology fails sometimes. It's
Technology
like sometimes
fails,
it's the most
exactly.
rudimental. Yeah.
Technology, their internet connection might be down. Maybe they got banned from BBC from looking at too many articles, right? Different things could happen, or they might have a stake, right? They're in this prediction market. They're about to lose $1 million, so they're trying to force through the wrong answer and actually kind of save their ass. You don't know. That's why you have this system of many validators that can kind of keep each other in check.
I mean, that reminds me of validators that human validators of other projects that actually did that, like what you just mentioned, prediction markets getting resolved by people who had millions and millions of stake in the same prediction, but then also it's kind of playing the judge, but also playing the game, but also playing the judge.
Exactly. We have a lot of inspirations for this, from other crypto systems where you have people voting on outcomes, to also from traditional human systems, from democracy itself as a form of government, from the legal system, right? The judiciary system, where you have a judge making a decision, but you can appeal it to bring it to a higher level court, and then in the end it gets to the Supreme Court, right, where you have multiple judges voting on the outcome. So it's inspired by all these humans, because we have thousands and thousands of years of people dealing with these same kind of issues, with biased entities trying to make objective decisions, trying to create this neutral system where we can trust each other and we can work with each other without having to have the private army of goons to go kind of back up, and break your legs if you actually screw me in some business deal, right? That's what we're trying to solve here. It's just a new way, but using a lot of inspiration from the traditional things.
And it has no border. That's the beauty of it, right? Like, it's kind of combining the beauty of smart contracts that have no border, that can be, enforced. Basically, the rules of the game can be enforced everywhere. But then you have like, okay, amazing, the smart contract can be enforced, but actually the smart contract itself is not that smart, because we realized that if-then logic probably isn't the best suited for flexible dynamic data. You and I have a contract. Maybe this contract includes one word more than the contract that you and someone else did, and all of a sudden the complete meaning of the contract changes. So you need someone to kind of assess the meaning and translate it into language that all of these
exactly.
Yeah.
And again, you think no, go ahead, Todd. Go.
Yeah, no, I didn't want to cut you off. I'm just trying to order also the questions that we have, because I think it is very important for the last few minutes to kind of draw the dots between what you have been explaining about non-determinism, determinism, follow the rules. So you have these LLM connected validators, and what's important to know is these LLMs connected to the validators are, as I mentioned at the beginning, all different LLMs. You have open source, you have closed source. Now, one question is, they are the heads behind making the non-deterministic, behind processing the non-deterministic data, the input, right? You can't just do that with any blockchain validator, with any node. Like, doesn't work on Ethereum, doesn't work on Solana. It works in GenLayer. So how important is the constellation of those of the LLMs attached to the validators? And do we plan to include DeepSeek? Actually, I think, correct me if I'm wrong, Edgars, that we have DeepSeek access through Hurist already, but I think you're better aware of that.
I'm not entirely sure if we're running it in, let's say, one of the existing test networks that we spin up, but the system is set up such, and that's the interesting part, maybe the unusual part, is that each of the validators are completely free to choose which large language model they want to use, including DeepSeek, including any sort of system, or including, it's not practically possible because of the speed these things happen. But, I said, imagine this with humans. In theory, you could have a human that's there, typing out an essay in 30 seconds, right, to resolve the whatever task is at hand. So it could be even humans. The way it's set up is that you have this economic incentive system through these rules of the game, that you're punished or rewarded for providing good answers. So you end up with this game that's also almost like inspired a little bit by BitTensor, for example, where you end up with this game, this competition between the different validators to get better and better at providing answers, and also, cheaper and cheaper. So the system is self-improving. We've set up incentives so the system gets better and more self-improving, and means each validator is free to use whatever model they want, even multiple models, right? For sure, we see that you're probably going to set up a router that, let's say, if it's a simpler transaction, you can use a cheaper model. But if it's a really complex decision, then you need to bring in the big guns. You need to bring in DeepSeek. So it's all about these incentives to provide good answers.
We have two questions that are going into the same direction, which is, let me just quickly pull it up. Here, how will we use the ZK Sync? I think stack was meant here for EVM compatible smart contracts to expand the functionality of its intelligent contracts. I think that's going kind of into the question of interoperability and how does this
it's interoperability, but it's actually almost like where I was going in terms of is the conclusion of what I've been telling all of you. It's connecting all the dots to completing the picture. So what I described to you is that you have these effectively two layers going on. So you have these GenLayer validators at the top with large language models, with web access, and you have this deterministic EVM ZK Sync layer underneath them, and they are all communicating and playing this game, this incentive game through the ZK Sync layer. But the integration actually goes a bit deeper than that. So first of all, the ZK Sync layer takes care of the rules of the game. It takes care of what I said, transaction ordering, right? If one validator tries to it's called double voting, when you try to tell some people that you vote for one thing, other people that you vote for another thing. It's actually one of is the highest tier of slashing that you can have in Ethereum, for example, because they're communicating directly with each other, and you can actually do something like this. And if it's discovered, you can be punished really harshly because it's like messing up the whole system. Well, in our case, this ZK Sync layer actually takes care of this transaction ordering in that, the contract says, okay, you can vote once. So whatever vote comes in first, only that's going to happen. So they can all agree on this objective state, on this objective. Where are we in the game? This guy has voted yes, this guy has voted no. Okay, it's a majority or not a majority. We can all agree because it's this layer that's keeping track of what's going on.
So just to make sure, the validators, the output, the lead validator posts, and what is evaluated by the other validators is done through, you have the validators here on the GenLayer, and then you have the ZK Sync layer, which is beneath that, and the validators kind of communicate through that layer with each other. So the lead validator is posting the output to the ZK Sync layer, and then it goes, and then the other validator knows, okay, that now it's my turn. I pick up the data, I do with the data whatever I'm supposed to do.
Exactly right. And we like to call this the overlayer, and this is the GenLayer chain. But exactly, again, you can, if it's easier, you can imagine it with humans in the game instead of these large language model validators. But let's say we're all using the same dApp, and this dApp has a UI. I'm sitting here and says, oh, there's a new transaction. Edgars, you're selected to be the leader. You have 1 minute to write out the answer in response to this contract, right? Or, oh, there's an appeal happening. You have 30 seconds to decide if the current answer that's posted is, if you agree with it or not, and kind of vote yes or no, basically, right? So you have all these things that are happening, and as a validator, I'm basically looking at this GenLayer chain layer underneath and seeing, oh, the rules of the game are telling me I need to do this. If I don't do this, I'm going to be punished. I might even be kicked out of the validator set, or at least put in the timeout box for 1 day, or all these kind of punishments. If I do it correctly, then I'm going to get rewards. I'm getting paid for this. So I'm monitoring all this game that's happening on this GenLayer chain layer. I want to speak more to the question that you have up here. So what is the EVM compatible kind of integration? Because that it goes into the interoperability with other chains, but even within this two-layer ecosystem. So we have what we call ghost contracts. I'm a big fan of this name. It's very evocative. But imagine you have all these intelligent contracts in this upper layer. This is the prediction market contract. Oh, this is the dispute contract for hiring blog post writers. Right? But each one of these contracts, we realized it would be very useful if they had a deeper integration on this layer underneath. So each one of them has what we call a ghost contract, which is the same address as the intelligent contract on this zk sync layer, and it can hold assets and it can interact with everything that's deployed on this EVM layer. So let's say you could have some automated market maker that's deployed on this EVM layer. Well, you could have an intelligent contract that holds some tokens in this ghost contract and says, oh, we're it's like an intelligent DAO contract, and there's some news event. We want to go and buy some uni tokens or whatever, right?
Mm-hmm.
So this intelligent contract, through the ghost contract, you can make a decision and then enforce this decision on this underlying layer and interact with other contracts on this underlying layer. And this is also how we achieve interoperability, because through this layer, you can also, basically on this layer, you can also have bridges like layer 0, like the zk-sync native bridge, which goes to Ethereum. It goes also to any other elastic chain in the zk-sync ecosystem, but also other like Caldera meta layer is another one of them. Hyperlane, all these different projects, well, they have ready to go integrations for the EVM. It will be much harder for them to integrate into this Python-based intelligent contract layer, but for the EVM layer, we can have everything like that out of the box. It's very easy to integrate. It's also very easy to integrate for existing projects on other chains. Well, they can use all these bridges, and they can also take their existing EVM code, again, deploy it on the GenLayer chain, on the zk-sync layer, and have the code working out of the box. And then they only have to deal with a smaller part of this novel intelligent contract side for this decision making.
Mm-hmm.
So that's the deeper level of integration that we have. These two layers are very tied together. You can query things that are happening on this layer from the over layer, from the intelligent contract layer. You can make decisions about things that are happening there, and you can hold ERC20 assets, and you can interact with ERC. You can interact with Solidity protocols and NFTs and everything that exists already, and tap into this huge ecosystem of standards and existing code and tooling that exists already for Solidity, and take big advantage of that. You can use another advantage. You can use existing wallets that all the kind of EVM wallets that work, with all the other EVM chains out there. They're going to work basically out of the box, at least with this underlying layer, and to some extent with this layer. It's not going to be perfect, but you're going to have quite a lot more compatibility than you would otherwise.
Yeah. Okay, Edgars, we have a few more questions. I don't know how hard this is going to be, but this is going to be a challenge right now for you. So Freaks is actually asking, can you explain the zk-sync integration like I'm 10? I'm just thinking.
I think. Yeah, how do we do this?
It's hard, especially in this constellation, right? Because I don't know if any like GenLayer chain, a GenLayer talking to zk-sync. It's almost like you're explaining something to a child, and the child can only say yes and no, and the yes and no is going to be picked up by someone else, and on that you kind of work through that. But it's just the first thing that comes up to my
mind. If I had to explain, I don't know. It's like, again, I like to go back to this board game analogy. We're trying to play a board game, something a bit more advanced. I don't know, maybe like Dungeons and Dragons and something like that.
Yeah.
And we're using zk-sync as the game master, as a really professional game master that's been in the game for a long time and knows how to do it best, instead of training one of our friends who was the first time playing this game, which would take a lot longer
that's a good
for them to get good at it. So we're using zk-sync, or even more precisely, I guess we're using zk-sync as maybe as a computer with hard, instead of having humans sit there and kind of try and keep track of all the rules, maybe then the zk-sync layer acts as a digital board game, right? It keeps track of all the rules, and then we can focus on just the decision making. We don't have to remember that, when you hit this turn, then you have to flip this other card, and we forgot 3 turns ago. So now, right? So it's like the
manual. It's like the manual for the board game. You have to follow what's happening.
Yeah, it's where the rules of the game live. Basically, that's where they're being tracked.
Amazing. Sheiks, I've seen your question. I think we've answered the Atoma partnership inference thing,
I see from
decentralized or centralized.
Burgermeister, yes, that is a good catch. That is a Ferrari behind me, and every year is their year. It's a sad thing to be a Ferrari fan. But I am a Formula One fan. Let me say it like that. I hope it goes well for them as every year.
I still remember, Edgar's, and I think you do too. When I was a child, it was the big days of Michael Schumacher and Ferrari winning everything. And I think everyone who was living through that era was kind of a Ferrari fan, or still is. But the last years have been hard. Yeah.
I'm always rooting for them. I mean, the cars are beautiful.
Yeah.
Such history. It's
Yeah.
fantastic. But they're always finding ways to kind of screw themselves a little bit. So
Yeah.
hoping for the best.
Yeah, that's right. Barrichello and Schumacher. Yeah, that's right. Okay. Yeah, Shrieks, I've seen your question. I would kindly refer you to the Atoma live stream we had last week. It's more about centralized and decentralized inference. We had another live stream on that like 6 or 7 weeks ago. So please feel free to check out that one. Edgar's actually is explaining how decentralized inference works and how we're using those partners, how we're collaborating with them. Okay. Edgars, thank you so much. We've reached the end of this live stream. If anyone has another question, I think we can still answer one. And I'm just going to post the POAP Mint link here. POAP Mint link. So prepare your phones. The wire is hot. The POAPs are, very, very, very popular. So I'm going to send it over now. This time it's Caldera minus GenLayer to celebrate this week's partnership. Again, we are going to have a live stream with James from Caldera next week. I think this set the stage very well for what's, I have to show the link. Sets the stage for next week. I think a lot of people will have a good explanation going into the Caldera integration for next week. And yeah, Edgars, if there's anything else to say, where would you point developers, users to use and kind of engage with GenLayer right now?
Always two main places to get started with. One is the studio, studio.genlayer.com. That's where you can get your hands on very quickly. You open the screen. It's a web-based development environment for GenLayer intelligent contracts. It runs in the browser. It connects to a hosted test network that we've set up for it with different validators. You have a ton of different example contracts, so very quickly you can just see hands-on. If you write any code at all, then it's going to be pretty understandable for you. It's Python. Even if you haven't worked with Python, then I find it's pretty easy to read, at least to understand at a high level what's going on. You can deploy contracts, you can interact with them, you can see how they're executed. And then, of course, the companion for that is always docs, our documentation at docs.genlayer.com. And there you can read more about the fundamentals of GenLayer and all the different components that go into the system itself, and also how to use the studio better, other different examples, and also more advanced features and more advanced use cases and other information, including also for validators and things like that.
Amazing. Or join us on Discord, where we also have our community events. A lot of stuff going on there. AMAs, community events such as poker, the GenFriend quiz. So we have a lot of stuff going on. There's something for everyone every day. Make sure to say hi, participate in the Interact campaign. We also have an invite campaign right now running on Discord. And yeah, that's it for today. Edgars, thank you once again. Thanks everyone for tuning in, and see you next week, Thursday, same time.
Thank you, everyone. Bye.
See ya. Bye-bye.